Hello everyone, I'm Jamius Siam and I'm from BRAC University, Dhaka, Bangladesh. Today I'm going to talk about our paper titled A Deep Convolutional Neural Network Based Anti-aliasing Technique for Real-Time 3D Applications. The main objective of this study is to propose a CNN-based anti-aliasing technique that is platform agnostic and can achieve an image quality similar to that of various modern anti-aliasing methods. I look forward to sharing our findings and hearing your thoughts during the Q&A session. Now let's proceed to explore the research in detail. Before we start, let's cover some background first. Anti-aliasing refers to the process of creating a smoother looking image from a source image that has jagged lines. These jagged lines often appear on the edges of a 3D object. To better understand it, here is an illustration of this phenomenon. Here you can see a line with and without any anti-aliasing applied. This problem occurs because there are not enough pixels in the image to represent a smoother line when it is being rendered. After removing the aliasing of the image, you can clearly see a vast improvement in the image quality. This is a simpler example, but the same principle also applies to any kind of real-time 3D application. Now there are several anti-aliasing methods that are being used industry-wide. Some of them include supersampling anti-aliasing, where we render the image initially at a higher resolution and then downsample. Multisampling anti-aliasing, where we supersample only the edge. Fast approximate anti-aliasing, which is a post-processing type of anti-aliasing technique that applies to the whole image. And temporal anti-aliasing, where it takes into account previously rendered frames among others. Most of these methods have their own pros and cons along with performance characteristics which we discuss in detail in the paper. Now let's talk about our proposed model. This is a sequential neural network comprising of 2D convolutional, 2D max pooling, and 2D transposed convolutional layers. The model takes an image as the input and produces another image as the output. The output is the anti-aliased image here. The arrangement of the layers of this model is outlined here, and the layer-specific parameters can be found in our paper. As for the loss function, we chose 1 minus SSIM because SSIM represents the similarity of two images in terms of a score ranging from 0 to 1. And by inverting it, we can use the resulting equation as the loss function. We'll talk more about SSIM shortly. We use the TensorFlow library to train this model. Moving on to the next topic, dataset. We used both Unity and Unreal Engine to produce our source images at 800 by 800 pixels resolution. Then to obtain the ground truth, we rendered the same images at 3000 by 3000 pixels and then used Adobe Photoshop to downsample those images back to 800 by 800 pixels again. Because of this, the end images look cleaner than the source image despite being the same resolution. Both of these image sets are then converted to black and white to reduce computation complexity while training the model. In addition to this, the images were shuffled and flipped, both horizontally and vertically at random. We had one training and one testing set for each game engine, and the details of the dataset can also be found in the paper. To determine the quality of the images compared to the ground truth, we used both SSIM and PSNR as the metrics. SSIM is used to simulate complex human visual system characteristics, whereas PSNR is the ratio between the highest possible signal power and the power of the distorting noise affecting the image. We evaluated our model and 5 other modern anti-aliasing methods with the ground truth images. Then the SSIM and PSNR scores were used to determine how our model compares to other methods, image quality-wise. It also has to be noted that some of the anti-aliasing methods that were possible in one game engine aren't applicable to the other, and vice versa, as we have used the reference implementation bundled with the engines themselves. We calculated the average values for both of these metrics from our testing dataset along with the variance. Ideally, we want a good SSIM and PSNR score along with less variance, otherwise one frame might look significantly better or worse than the next. In our experimental analysis, the model exceeds all other tested methods in terms of SSIM and PSNR scores, as can be seen in these charts. Data from both game engines are included here. The raw images expectedly have the lowest values in both metrics, with various methods having different scores. Now, performing better on average isn't enough, and we also need to look at the variance as well. These charts show the variance of our model along with other methods. It is evident that the median scores of our model are considerably higher than those of the others. There are some deviations, but most of them are in the higher percentiles. Along with image quality, we also need to take into consideration the performance characteristics of our model as it needs to run in real time. To achieve this, we converted our TensorFlow model to the Open Neural Network Exchange format. Then, using the Barracuda Neural Network Interfacing Library developed by Unity Technologies, we can run the model with the help of some compute shaders to perform the black and white conversions. The rendered frames of the game engine are then fed into the model and the outputs are displayed on the screen. We ran our model on various graphics cards and the performance data from them is displayed here. As we can see from the chart, most of the mid-range cards from the previous generation can run the demo game scene with 30 frames per second or above. Even a flagship GPU from 3 generations prior can achieve around 40 frames per second on average. With the current generation of GPUs, we can expect even better performance from the model. The computation power required is also not dependent on the scene complexity, as our model basically works like a post-processing effect. Considering all of this, our model achieves the minimum performance level of 30 FPS or more, enabling real-time application of it. In conclusion, we proposed a real-time CNN-based approach to solving the anti-aliasing problem, and our analysis shows promising results. The SSIM and PSNR scores are higher than the other methods, and our model can run in real time. But there are some areas in which further work is still needed. Firstly, the model only works with black and white images now, and we need to add full RGB support. Secondly, the performance of this model can be further optimized. However, despite these limitations, we believe this lays a solid foundation on which further research can be conducted. Last but not least, we would like to express our heartfelt gratitude to our advisor Dr. Uddin for his guidance and advice, and this work wouldn't have been possible without his support and encouragement. Thank you all for your time. Please let me know if you have any questions or comments, and don't forget to have a nice day.